Hi, I'm Randall Heyman, a mathematics academic. Welcome to my Corona Help playlists, where I make quick turnaround videos to help people during the coronavirus outbreak, all for no charge. If you'd like me to make a video for you or your students, then contact me by email or comment below any of my videos. So today we've got here, someone's asked me, Michael actually, this question, it's what I call a harder induction problem. Why is it harder? Because if we look at the problem here, we've got this total or a sum of the first k terms of this series here. And we're told that the sum is a certain thing, -8 times n squared if k is 2n, so if k is even, but it's a different one if k is odd. Here, k equals 2n plus 1. So this is that makes it a bit harder than the vanilla standard induction problem. So I do have a video called let's put that in blue, Proofs Made Easy, where I go through induction, because induction is one of the major forms of proof. So have a look at that if you really don't understand much about induction proofs. If you do understand induction proofs, well, I'll just make a comment here first before we start, and that is the basic idea with induction is that we might start with, we want to show that it's true for n being any positive integer. And what we'll do is we have the initial step, which is to prove that this is true. It's true in the case of n equals 1. And then we have the induction step where we just have a variable k. We say assume that it's true for k, and then we show that if it's true for k, then it's true for k plus 1. And once we prove that, we're essentially done, because if it's true for k, if when it's true for k, it's also true for k plus 1, then we can go back here and we can say, well, it's true for n equals 1, so it must be true for n equals 2 because of this rule. And if it's true for n equals 2, it must be also true for n equals 3, and et cetera, et cetera. Now, the difference here is that we can't do it that way. Well, actually, that's not quite true. We could do it that way, but there's a complication because of what I said back here. We've got different sums depending on whether k is even or odd. So what you could do is you could say, okay, let's say k is, down here, k is odd. And I'll prove that if k is odd, then k plus 1, which is then even, of course, that's true as well. And then you could separately do what happens if k equals even, and prove that if k equals even, then k plus 1, which will be odd, is true. You could prove that. And then back here, you'd have to have, as your initial steps, you'd have to do n equals 1 and also n equals 2. And the combination of all that would be sufficient to prove it. But what I think is an easier way to do it, certainly for me to explain it, I think is that what we'll do is we'll do it as almost like two problems. One will do k equals, so the one I'm going to do actually is, what do I do? I'm going to suppose that k is odd. So there's two cases. Obviously, k is even, k is odd. So I'll just do the k equals odd case. So for the k equals odd case, what we'll be doing is we'll be showing in the initial step that it's true for n equals 1. And then we'll be showing that if it's true for some k odd, then this one, we won't be doing this. We'll be showing that if it's true for some k that's odd, it's also true for some k plus 2, which will also be odd. And then we'll go back and we'll combine, if that's true, then the combination of the two, the initial step and the induction step, gives us what we want, because that means that if it's true for 1, it must be true for k equals 3, k equals 5, k equals 7, etc. So that will then do the k equals odd case, and then we'd have to do a k equals even case as well. So I'm just going to do the k equals odd case, because otherwise the video will be too long. the other problem you have with this is that it gets a bit messy with the K's and the N's, you'll see as we go. You have to keep a very clear head on this. Okay, so let's see if we can, we'll rub this out, which is just all the commentary, and we'll launch into a sort of a solution to this. Okay, so let's do that. So this is how I would set out a solution. Let PK be the proposition that let's say the proposition that the summation formula is true for the first K terms. Now, I know that I'm going to need this. What we have to do is work out what's the kth term back here. And if you play around with it a bit, I mean, the first thing is it goes negative and positive. So let's just write that up here. The kth term in the series, well, the kth term of the series is probably more accurate, better grammatically. But anyway, we know it's going to have a -1 because it's got to change sign every term. So this is going to either be K or K plus 1, the power of -1. And in turn, it actually turns out to be K plus 1. You can go back and have a look at that. I mean, if K equals if K equals 1, the first term, well, the first term is positive. So this K equals 1 here, we go K equals 1, 1 plus 1 equals 2, and -1 to the power 2 equals +1. So that gives me the correct thing there. Now, the next thing is when we look at the terms back here, they're all odd. So I know that the way to get odd is to go 2K. In fact, I know it's an odd number squared. So I know it's going to be either 2K, it could be here, this could be +1 or -1 or +3 or -3 or whatever. But by just looking back here, we can see, I know it's squared, we can actually see that it's actually -1. So actually I'll rub all that out and just write 2K minus 1 all squared. Okay. Okay, so now I'm going to do the odd case. Suppose K is odd. Okay. So what does that mean? So K equals 2n plus 1 for some integer n. So here you can see the problem that I hinted at before. K equals 2n plus 1 for some integer, which is the normal way you would write an odd integer. Back here we've got K equals 2K minus 1, which it has to be 2K minus 1 in that case. So I mean, this one, yeah, anyway, it sort of starts to get a bit complicated because of that. Anyway, okay, so let's now do the initial step. For K equals 1, so the first term, that's the first odd term, we have n equals 0. That's when I look back here, n equals 0, if I want to make K equal 1. And what do we have? 1 squared, because that's the first, that's the sum, that's S here, back here. And what does that equal? Well, it equals, we're expecting it to equal this because it's odd. And so n equals 0. So it's 8 times 0 squared plus 8 times 0 plus 1. So I suppose what I'm saying is, what I've shown is that P1 is true. Remember, we defined P back here. The proposition that the summation is true for the first one term So P1 actually, I shouldn't write B0, is true. Okay, good. So we've done that initial step. Okay, what about, obviously the next bit is a bit more complicated. Okay. So then assume PK is true. And I wouldn't write this if I was doing it, but I'm just writing it so you know this sentence. Then assume PK is true. Next, we will show that PK plus 2 is true. Okay, so that's the idea. We've shown that it's true in the case of the first one, P1. Now we're showing that if it's true for K, where K is odd, then it's true for K plus 2, which is also obviously odd. So if you think about it, what I'm going to have to do is show that the formula works for PK plus 2. So what I'll do is I'll create PK plus 2. So to do that, I go 1 squared minus 3 squared plus ... all these terms, plus the 2k minus 1 squared. That's the last term. That's the k stuff. That's showing, that's the k. And now I'm going minus 2k plus 1 squared plus 2k plus 3 squared. So this is sort of the first k terms, and this is the next two. I don't think I'll leave that up because it's going to interfere with everything, but that's the basic idea. And now what I know is I need to end up with this down the bottom with the formula, this formula here, back here, this formula here. I've got to get this formula somehow, but it won't be for n, it'll actually be for n plus 1. Okay, so that equals, well, this bit, this first bit, I know by assumption because we know PK is true. So this is 8n squared plus 8n plus 1 minus, and then we take off this 4n plus 3 squared plus 4n plus 5 squared. So where did we get that? So you wouldn't have to write this necessarily, but 2k plus 1, we've got this 2k plus 1 here, and we said that k equals 2n, what did we say? K equals 2n plus 1. So since that, and k equals 2n plus 1, so 2k plus 1 is the same as 4n plus 3. So that's how we get this 4n plus 3 here. And the same with that one there, the 4n plus 5. So this is what I was saying before. This gets quite complicated because of all these k's and n's. Okay, so now I've got everything in terms of n. You see what I didn't like having these k's here because it interfered with what it interfered with this line. Well, sorry, the problem here is I've got k's and n's. Here now I've got all n's. Let's just leave it at that. So now I can just expand minus, so this is 16n squared plus 24n plus 9 plus, and I can expand this 16n squared plus 40n plus 25, and this will equal 8n squared plus 8n plus 1 plus 16n plus 16, and that equals 8n squared plus 24n plus 17. And I know where this is heading. It's heading to, this is what I want it to be, n plus 1 plus 8n plus 1 plus 1. So you can see here, this is now of the form that we needed from back here, this thing here. So So this tells us basically that this is the sum, as it should be, for k plus 2 terms. Remember, this is, once again, this is in terms of n, but remember k equals 2n plus 1. So when you look at that, we can conclude that that is the formula you would expect for k plus 2. So p k plus 2 is true, and therefore the sum to k terms of 1 squared minus 3 squared plus 5 squared minus ... where I think we had k equals, in the question it said k equals 2n plus 1, didn't it? Yeah, 2n plus 1, where k equals 2n plus 1, bracket, comma, comma, is 8n squared plus 8n plus 1. And if you want, you could put by induction. I know in high schools in Australia, they're often picky about how these induction proofs are set out. So you might have to write that in. And then, of course, next, you would do k is odd. The k is odd case, which I'm not going to do. But that's how I would go about setting this out. And if you did what I've done, you probably, I'd pretty, well, as long as you conform to the way you need to set out the induction proofs, then that would get you full marks. Okay, so let me just roll that up to the end. Hope that's been helpful to Michael, and I'll stop here.